Okay, what do we have for this shape of the table? What's it based on? Okay, reactivity. What's it not based on? You okay with that? It works because of electrons, but the development of the table had nothing to do with electrons. How do we know it had nothing to do with electrons?
Because it was developed before the electrons were discovered.
It was developed by a guy who actually didn't even believe in electrons. So, yes, before electrons, and then once the electron was discovered, he did not believe that was actually what was going on. So this has nothing to do, its actual creation had nothing to do with any understanding of electrons. The reason that it all works out is because of electrons, but that has nothing to do with where the development came from. How many energy levels? 7. How does this relate to the table? 7 what?
Rows.
7 rows. Did you say rows first?
I said groups.
What's a group?
The A or the P or the.
No. Anybody know what a group is? Columns. The columns are groups or families, so that would actually, just make sure you don't make that mistake.
Don't break that on Thursday.
On Thursday. Especially now. How many sublevels exist?
7.
7. S, P, D, F, G, H, and I. Why are there 7 of them? And what does 7 rows imply? There's 7 energy levels, and every single energy level has its number of sublevels. So how many energy levels have energy level I or sublevel I? Just 1, just the last one, just 7. Now, I know that I had said earlier that G, H, and I aren't used. I didn't exactly say it like that. The way that they're not used is they're there, but they're empty. So there was the discussion that we had about putting the Sears Tower into downtown Hood River. Many of those top floors would obviously be empty because there aren't enough people to fill up all those spaces. But the spaces still exist. So even in the hydrogen atom, there's definitely an I sublevel in the 7th energy level. It just doesn't have anything in it. And we don't have any atoms that have so many electrons that in their ground state, meaning the state where they like to be under normal circumstances, the electrons would never find their way into a G, H, or I sublevel. But having said that, if you get the thing excited, what will the electrons do? Jump. They'll jump up to those empty sublevels like G, H, and I sublevels, and then they'll fall back down to where they were before. So they exist, they just are normally unfilled. How many electrons fit in an orbital? 2. Which sublevels are found in energy level 2 and why? S and P and why? Whatever energy level I'm in, you have that many sublevels, and the first 2 sublevels are S and P. So energy level 1 only has 1 sublevel because it's energy level 1, so it has an S. Energy level 3 has 3 sublevels, S, P, and D. So energy level 2 only has the first 2. How many electrons will fit in that 4th energy level? 32? 32 because it's S, P, D, and F. and this is 2, and this is 6, and this is 10, and this is 14. So these two things make 20, and then there's 30, and then there's 32. Electron configuration for nitrogen, we've got 1s2, 2s2, 2p3. Two ways you can confirm that that's true. You can add up the electrons, and it's 2, 2, and 3, giving you 7, and nitrogen is element number 7. The other way to do it is that last electron, it's in the second row in the p block, and in the third column in the p block. And then you do all that, you find yourself at nitrogen. Sulfur. We have 1s2, 2s2, 2p6, 3s2, 3p4, 10, 16. Yeah, so if we had 2, 2, 6, 2, and 4, you get 16, so that's sulfur. And then if you find yourself in the third row, the p block, and the fourth column over, you'll find sulfur.
So we should write it that way, not NE first? Well, the whole thing,
What did I ask for?
the electron configuration.
And what did you write?
I wrote NE 3s2p4.
And what do we call that? Somebody said it. Go ahead.
Noble gas?
That's the noble gas configuration.
Oh, okay.
If I asked for the shortcut, which I did later on in this, then
Yeah.
definitely write that. But
Yeah.
since there was no, you need to write the whole thing out.
Okay.
1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6. And so 2, 2, 6 is 10, it's 26, and iron is element number 26. So we're good with that. And the third row, except since we're in the D, it's the fourth row, the D block, and the sixth column over. Okay. Hund's rule. What's the explanation for Hund's rule?
That's where electrons will fill up orbitals without any electrons in it first. That's Hund's rule.
Sure. A little bit more to that. You need to say something about something like that. So if you have a sublevel and it's got multiple orbitals in it, you put one electron in each orbital before you start pairing them up in the same orbital. And the reasoning behind that is, if I'm in a sublevel with multiple orbitals, every single one of those orbitals has the same amount of energy. And so the electrons push each other away, one in each orbital. I was just looking through the homework, and some of you were looking up some of these answers online, and some of the answers that you were giving were not, we definitely didn't discuss the verbiage that was used, and I seriously doubt you could explain what you wrote, so don't do that. The basics for the Pauli principle state what?
The electrons spin.
Okay.
Because they're negatively charged, they spin in opposite ways and opposite directions. So like upside down to each other.
Okay. Electrons have spin. Electrons in the same orbital must have opposite spin, so they generate opposite magnetic fields. So the stuff about having fermion, all of that, I'm not sure you guys, whoever wrote that, can explain what those things are. So just stick to its. Why would you want to generate an opposite magnetic field? Opposite magnetic fields attract, right? So if I've got an electron that's a negative charge and an electron that's got a negative charge, if I've got a north pole here and a south pole here and a south pole here and a north pole here, these things are attracted to each other. These things are attracted to each other. And that only happens when one of these electrons is spinning one direction and the other electron is spinning the other direction. Uncertainty principle? What are the basics with that?
Does it have to do with something about mathematics?
Nope.
No? Okay.
So basically, you can never know the exact position and speed of something at the same time.
Okay, so Heisenberg's exact definition was you cannot know the momentum and position. Yeah, spell that right. You can't know the position and the momentum at the same time. That's a fancy way of saying you can't see one. Why?
Because any light used to try and view it under any sort of microscope would physically move the liquid.
The act of observing it or looking at it actually moves it. So every time we go to look at it, it's not actually where it was. This seems a little ridiculous because you can obviously like watch a baseball fly through the air. There it is, and it's going that fast. But us looking at it, the sun that hits the baseball and ricochets to our eyes isn't powerful enough to move the baseball. Whereas an electron, if I'm trying to look at it, if it gets hit by a ray of sunlight, the electron gets scattered into a completely different direction, and we won't actually be able to see where it is. Write the shorthand notation for an electron configuration. Why do you have to go to the last noble gas? So what's the deal with the last noble gas? What do the noble gases have to do with electron configurations? So we're talking about filled, stable sublevels. So if neon, for instance, has its S and P's filled. So that configuration is very stable. So if I add one electron to it to go on to sodium, that one electron is unstable in its position, where the 10 underneath it are stable. So they're sort of plateaus of electron configuration, way stations. You get to a point and this is stable. If I go a little bit further, it's unstable until I reach the next plateau where it's stable again. I guess kind of like summiting Everest. It's precarious, and then there's this flat spot where people hang out for a while, and then it's precarious again, and then there's a flat spot. And so that same situation happens in where electrons are found in atoms. So we're going to do the noble gas configuration for titanium. So titanium is 22. If I back up to argon, that's 18. That'll be my last noble gas. So Ti, and then Ar in brackets, and then 4s2, 3d2. And that'll put us in the second column in the D block for titanium. I have a feeling you guys had a different homework than I have written right here. Did you have that?
No.
That last question you didn't have?
Yeah, we did.
It was in a different spot?
No, there's two different questions after it, which column is the name knowledge
Okay. 6. All right. We had, which column is named the halogens? Okay, so which column is that? It's either column 7A or column 17. Either one of those is fine. And they're used for what mostly? Say again?
What was your first name?
Disinfecting.
What are they used for? Disinfection? Yep.
Lighting.
Disinfectant, lighting, and salts. Okay. Which are the alkaline earths and why are they named as such? So they're 2A or column number 2. And they're named as such because raises the pH. So if you put magnesium in water, the water's pH will go above 7. Same thing with calcium and everybody else in that column.